Yeah, first of all, thank you for coming to this talk. And I promise you won't regret it. But if you do, I will buy you a beverage of your choice. And if you're watching this online, that's on you. The title of the talk is From Service to Platform. But I like to say this talk is about the single method interface in Go, refactoring, and a few other surprises. So keep this in mind. I was told you should start a presentation with a story, so here it goes. Once upon a time, or more like around this time last year, I was investigating one of our Redis clusters. A node had a higher CPU utilization than the others. If you leave this unchecked, it might continue to climb to the point where the node fails entirely. To avoid this, I wanted to get a better understanding of what is happening. For this, you can use the Redis monitor command. It provides a log of key access in real time, containing a timestamp, the database, network address, but most importantly, the command and key. Ideally, the log looks like this, different keys distributed across different nodes. On the other hand, if we see something like this, not so great. Too many keys with the same name are being accessed on the same node. This is called hotkeys. To find hotkeys, we could write a program which counts the number of unique keys. Something like this. We read the whole file into memory. We parse each line, splitting the columns by whitespace, and count each key using a map. Finally, we convert the map to a slice and then sort and print out the most frequently used keys. We compile this and run it on the log file. We get this, which is perfect. This is exactly what I wanted. On the top, we see the key that is just located on one node, and that is something we can focus on improving. So you might hear I don't sound too exciting about this, do I? Because I never wrote a program like this in the first place. Because this is what I use. Boom, Unix pipes. They combine programs that take an input, process it, and output it to the next program. The only reason this works is because of the Unix toolbox philosophy. Don't add new features. Instead, write a new program, but make it compatible. This talk is about complexity, and here we have dealt with complexity head-on. You see, in software engineering, we talk about essential complexity and accidental complexity. Essential complexity describes a problem at its core, something we cannot change. If we need to find the most frequently used keys, then that's what we have to do. But how you go about solving the problem creates something called accidental complexity. This can include writing overly difficult code, writing code which is slow. In other words, we're making our life harder than it has to be. Accidental complexity is something that can be reduced. If our implementation is slow, we can make it faster. We can write code to solve a problem, or we can reuse existing tools. This is not a new concept. This idea has been around for, at the very least, 36 years, and you can read about it in this paper, No Silver Bullet. It probably goes even further back to ancient Greek philosophy, Aristotle's classification, but just not directly about software. Go is a language that helps us naturally to reduce accidental complexity through the language design and its philosophy. Writing idiomatic Go code means to write code that has less accidental complexity. And I'm going to show you why this played such an important role for us at Reddit, how we design and implement recommendation pipelines. In my role as a software engineer, I work for the ranking platform team at Reddit. And for those of you unfamiliar with Reddit, it can be described as a platform where people come for the cats, but stay for the communities. Or in this case, dogs. Really anything you're into. With a lot of content posted every day, we need to figure out how to get this content to the users. This can be described as a machine learning problem, but it is also a software engineering problem, which is what I'm going to focus on in this talk. So some of you might have come to this talk to learn about recommendation ranking systems. And this guy talks about Redis in-memory cache and Unix pipes. You wonder what's going on here. So let's cover the basics. What is a recommendation system? A recommendation system helps users to find content they find compelling. And this can be described in 3 steps. The first step is candidate generation. And candidate here is, or candidate is a fancy word for referring to the content being ranked, for example, posts. But it's called candidates because you could also rank other things. You could rank topics, you could rank users you want to notify. Then there will be some candidates we want to remove. For example, posts the user has already seen, or posts from topics the user explicitly said they don't want to see. So we have a filtering step. And then finally, in a third step, scores are assigned for the purpose that we're able to sort the candidates before sending them to the user. Okay, how does this translate into real life? On the right side, this is what we want to create, a feed for the user. We already have a data store that provides us with popular posts. That's great, because now we can fetch those posts. That's our candidate generation. And because we don't want to show the same posts over and over again, we want to filter them out. For this as well, a data store is managed that provides us with posts that give us those candidates that the user has already seen. And then finally, assigning scores for the order. And we could do this based on a heuristic, something like upvotes minus downvotes of a post. Or we can do something more personalized and run it through a machine learning model. And there we go. That's all we need for now. Because you see, it doesn't stop here. I mean, it never does it? With ranking systems, you want to iterate, add features, see what works and what doesn't work. For example, we decide there should be more video content. Okay, now we might have to worry about duplicates, duplicated posts between these different data stores. So we need to extend the filter stage as well to take care of that. So we can say ranking systems are prone to experience a lot of changing requirements in a short period of time. Let's say you get to implement this in Go, and this is what you wrote. A service exposes a method called getPopularFeed. Here we fetch the posts, and it's great, you already moved this into a separate method. Then we filter posts, run it through the model to assign scores, and then sort and return them. The thing is, when you first wrote this code, it didn't look like this. There were no helper methods, but as you were asked to add more functionality, you started to move this code out. And why did you do this? Well, you want the code to be maintainable, right? And by now, you should slowly start, hate me saying this, but maintainable code is code with less accidental complexity. So we can say continuous refactoring is our tool of choice to keep the code in this state, to keep the code maintainable. And we do it because it allows us to focus on the tasks that deal with the essential complexity. The problem is, not everyone makes time for this. You get assigned to a different project and someone else gets to pick up your work. Oh boy. They're asked to include image posts now in this ranking pipeline as well. So let's make some space for them. The person has no idea what type of code structure you had in mind. In fact, they're in a rush. They just want to get this out quickly and be done with it and attend to their favorite project. I don't blame them. They see the fetch post helper method that you've set up here, but they don't want to modify it. They didn't write it. Why should they touch it, right? They just decide to drop the code right here. Rude. Okay, why would you care about this? You can come in and clean this up at any given time, right? But maybe this won't be the last change before the next person shows up and follows the lead of the previous change. Can you imagine how the code will look like? It might not fit even on the slide anymore. It's terrifying. It terrifies me. It terrifies me in an environment like a ranking service which faces constant changes under constantly changing requirements. I mean, who's going to do all of this refactoring? You? Me? Him over there? I don't know. How many story points do you have left in your sprint? At Reddit, we asked ourselves, is there maybe a way we can limit the number of times we have to refactor through a structural design? Let's think back to the Unix pipe example. Wasn't it wonderful how we could just combine and compose these different programs? And now let's look at this. Looks awfully similar like Unix pipes. So let's generalize it. Everything just becomes a stage, a step in the ranking algorithm. And this is how we can write it as a Go interface. A stage takes a request, and to match the Unix pipes analogy, it also returns a request again. And this works because our request carries the request and the response. As the ranking progresses, candidates are added or removed. And we use an entity to describe the context as well as the candidates. The context provides us with information what we are ranking on. For example, the context could contain the user making the request. And entities can be used for both purposes here. An entity provides an ID for unique identification, for example, a post ID. And it has a list of features. Feature, again, one of these fancy machine learning words. A feature refers to a property, an attribute of an entity. For example, a feature could be a list of a list of topics that the user likes. So it gives us information to make better ranking decisions. And then we have a score, because we want to be able to sort candidates and provide an order. Some of you might have noticed the package reference PB here. It stands for protobuf. And I just want to point out, this is an implementation detail. The ideas I'm going to talk about here are still hold true even if you don't use protobuf, but I thought it's interesting to share. Because those type definitions that we use for the interface come directly from the Go code that protobuf has generated. Our ranking service is defined in gRPC, exposing exactly one method, rank. And request is defined in exactly the way we just saw. What's nice here is that for features, we use protobuf's one-off semantic, which allows us to encode a fixed set of types into the same field, but only one can be set. And an example request could look like this. The context is set to a user ID, and then we provide location-based features in order to recommend content to the user that is more specific to their geographic location. We also specify a method under option because our service is just one endpoint, so we need a different way of providing this routing to different ranking pipelines. Now, with this interface setup, our gRPC server implementation looks embarrassingly short, because the stage interface matches our service method signature. At Reddit, we developed this as a prototype for doing ranking, and we called it Pipe Dream. A ranking pipeline on Pipe Dream is an acyclic graph of stages. And if we think back to the previous example and translate it to a graph of stages, then now we have these different fetch posts happen in their own stage. Those stages perform network requests. They could go to a service, they could go to a data store. Network requests are a great excuse to use Go routines. And I always like if I have an excuse to use Go routines. Go has great concurrency features, but managing the lifecycle of a Go routine is not easy. It's so easy to drop those two letters in front of a method. But how you manage things like graceful shutdown, context cancellation, a lot goes into that. So we can extract the implementation detail of concurrent execution into a stage as well. And so now we talk about stages that execute other stages, meta stages, stages of stages. So if we want stages to be executed in sequence, we wrap them in a series stage. If stages should be executed in parallel, we wrap them in a parallel stage. This way, we take care of executing Go code concurrently and correctly so that developers can focus on the business logic, the details of the ranking algorithm itself. And so this way, a whole ranking pipeline can be pieced together. Oh, who did that? I feel like a colleague pulled a prank on me. This looks nice, but I just want to point out that the semantic here is implicit, because the interface or type system doesn't enforce any of this. So with that, it gives us a lot of flexibility, but it also requires us to act responsibly. Okay, that's too many charts. You probably think, if you want to see charts, I'm going to draw an architecture diagram for my manager. So let's take a look how this would look like in Go. For example, fetch popular posts. Okay, a struct implements the stage interface. And each stage has only the dependencies it needs. And we pass in the dependency through the constructor. By the way, this is my favorite dependency injection framework. Just do it manually. Okay, here we fetch the posts, and then we add them to the request. So a stage always operates on the request type to make changes. That's why it has a pointer type. Okay, what about filtering? A previous stage has set up a map that contains the list of recently viewed posts. And so we can use this map to remove any candidates the user has already seen. A fast implementation would perform this with in-place filtering. Okay, what about meta stages? Meta stages are really the glue that holds the ranking pipeline together. For example, the series stage. It holds substages in a field, and the initial response is set to the request. And then each individual stage is executed in sequence. But the important part happens here. We set the input of the next stage to the response of the previous stage. More complex is the parallel stage. Okay, well, a lot of things going on here. So we don't use Go routines directly. Instead, we're using the air group package. I generally always recommend that you write your own concurrency primitives. I often find that there's always something small I want to work slightly different, and only you know really the aspects of how you want your code to run concurrently. But in this case, I ended up pretty much with the same implementation, and so it was nice to reuse it here. So the error group is a sync await group that also handles error propagation and context cancellation for us. Okay, so each stage is called in its own Go routine. And here we pass a copy of the request to the next stage. Why do you think we do this? Because each stage might modify the request. And so we copy it to avoid data races or having to synchronize access to it at all. Okay, and then we block and wait until all Go routines are finished. And then, because we copied the request, merge all responses back into the original request. A meta stage doesn't always have to contain many stages. We can also think of a meta stage that takes exactly 2 stages. An if-else stage. Based on a selector, we execute either one or the other stage. Okay, all of these stages form a pipeline, and what I really like is that we're able to define these pipelines in an expressive way in Go. And you can think of this as a domain-specific language, but that's not the purpose here. The purpose for us is to make it easy to understand what is happening at any given time in a ranking pipeline. We want people to be able to look at a pipeline and have a pretty good understanding of how the ranking algorithm works without having to dig through the code and the details. Okay, we're still talking about a service here, but the talk is titled From Service to Platform. I think I have 19 minutes left, so let's better get to it before I get into trouble by the organizers. That's not fun. Okay, when does a service become a platform? I'm sure there are plenty of definitions out there, and because of that, here's mine. With a service, your customers are the users or product management. With a platform, however, your customers are other engineers. Engineers that use the platform to develop their own services, their own offerings. And to be a platform means to think API first. And when I say API, I don't want you to think of something like this here. No, I don't mean your typical REST API. Nothing wrong with that. I'm talking about this here. If you create a package with exported types, exported identifiers, it becomes part of your API. This defines the boundary of your API. This is part of your API. Those two are. This is not. So how come we export identifiers so carelessly? Can you do me a favor? The next time you have to decide whether an identifier should be exported or not, imagine you have to set up a REST HTTP endpoint and you get to maintain it for, let's say, the next 2 years. Doesn't sound too great, does it? So if in doubt, just start unexported and make the decision for exporting identifiers based on how you want them to be consumed on the site that will import them. We are aware of our API. It's visible here, defined by what the stage package exports. Working with this as a small team is manageable. Our prototype service was built to rank the video live stream feed for Reddit. And we added more pipelines, other product services, but it was us who built and maintained them. Soon enough, we would start to onboard other products, other product services outside of our team. And this is really the moment that marked for us the transition from service to platform. Because to scale this, you need to have other engineers outside of your team to build those pipelines as well. But we help and we guide. So we have a base of existing stages, but then each product comes with its own unique set of requirements, which is completely normal. They have to add new stages in order to be able to build their ranking pipelines. And as a platform, we need to make sure that new stages can also be used in other pipelines. Why? Well, Unix pipes only work because of the principles how a program should be written. And so these are our principles for designing stages. Limited scope, clear naming, decoupling, strive for reuse. Let's illustrate this on an example. This stage fetches image posts. Does a few other things. It also shuffles the candidates. If you ever find yourself writing like a recommendation algorithm, like shuffling is a really great way to create feeds that always look slightly different. Okay, back to the principles. Let's start with the principle of clear naming. Image posts. A stage should be named after the action it performs, so let's put a verb in front of it. We can call this fetch image posts. That's a lot more clear. The next one is limited scope. The shuffling that happens here doesn't have to happen in exactly that line. There's going to be a lot of other pipelines that will also want that functionality, so let's kick it out and move the code into its own stage. Limited scope also helps us with having a compact stage that when engineers look at this, they very quickly get an idea of what is happening without overloading it with additional functionality. Okay, next, strive for reuse. We want to increase the chance that someone else is going to include a stage in their ranking pipeline. Sort of increase the toolbox that is available. And so the key used to look up this feature is something, we don't have to hard code it here. Subreddit IDs, that's IDs of different communities on Reddit. We can turn it into a parameter and make it configurable. And then finally, for decoupling, we might not even want to rely on this feature being available in the first place. And sometimes that means to make other APIs more flexible. Those guidelines exist to ensure contributions to the API maximize for reuse and clarity. Reuse and clarity, though, are competing goals. If you over-optimize for reuse, you will sacrifice clarity. And remember, this is Go. I will show you how we deal with this. Okay, Rob Pike said it first. The bigger the interface, the weaker the abstraction. Put differently, the fewer methods an interface has, the more useful it becomes. Having every operation be represented by the same interface, the same method, gives us another benefit. We can have a function implement the interface. A function type declares the same method as the interface. And this is useful when one stage in the pipeline is just too specific for other pipelines. So instead of creating a new stage, we can define it right here. No commitment. We avoid having it become part of the API or any discussions around whether it should or should not be part of the API, allowing other colleagues to ship their products. We can consider this an escape hatch. This also works for middlewares. And a middleware for us is a stage that wraps a stage. And middlewares is something that really provided us with great payoffs in this kind of ecosystem, especially for running code in production. And here are 3 examples. Okay, this is a monitor middleware to record the latency. Recording the latency of an endpoint of a service is pretty standard. You should do it. But here we record the latency of each individual stage. What does that mean? For us, it meant that the profiler became obsolete, because we're able to see which part of the pipeline takes the longest. So we are able, while the code is running in production, to see what stage should we focus on next to optimize in order to improve the overall latency. The next middleware helps us with diagnostic, a logging middleware. We use the deferred function statement to only log if a stage returned an error. And this is great when you use structured logging, because our request type already has this generic makeup. Or even if it doesn't. If you use protobuf, we can use proto.json to just log the entire request. This is great because there is no need to modify, add any information if you're debugging something. You just get the full picture. But please keep in mind this can, at the same time, be very dangerous. Depending on where you operate, you don't always want to log everything, right? It could include information like we've seen geographic information of a user, which is considered personally identifiable information. So again, to the point, a lot of flexibility, a lot of responsibility. The next middleware the third one helps us with incident management. We can change a lot of our configuration without having to deploy using a dynamic configuration system. This can be used for stages too. Okay, a stage starts to create issues in production. No problem. You can just turn it off and it gets skipped. So no custom code required to add additional code to feature flag new code paths. And no rollback required. A software reliability engineer wouldn't like that statement. All of this is not to tell you, hey, you should structure your ranking system or any system exactly like that. Many of us need to write a lot of code every day. We're expected to deliver and produce output. And one of the reasons why I really like coming to conferences is because it's just a time to lean back and breathe in and just get a little bit inspired. And I hope this talk is an inspiration for how we can make use of Go. We use this design to make sure we build small and reusable components from the start. So as we've seen, it doesn't eliminate refactoring, but it gives us a framework for refactoring. And middlewares have a multiplier in this kind of system, which can make running code in production a lot easier. As long as it's just your team, it's not a platform. I'm sorry. Platform starts with the developers contributing code that do not have the same context that you have. And providing an opinionated framework like this one will always create friction. This can be confusion or disagreement. And there may be like 3 ways to deal with that, and guess what? None of them are right or wrong. You can bend the will of your contributors to your will. Sometimes that's necessary when there is a learning curve. But maybe you're wrong. Or it could be a sign that you need better documentation. No one likes a second one, but sometimes necessary to ship code to production, to ship a product. And third, well, you find the time to rethink the existing approach, which is great, but not always feasible. Okay, with this in mind, what is left? Or rather, what's next? One of them is error semantics. If we think back how the parallel stage is implemented, once a substage fails, it fails the entire pipeline, the entire parallel pipeline altogether. That's a bad thing, because we don't always need the whole pipeline to succeed to produce a feed for the user. And a degraded feed is better than no feed at all. So one idea would be to provide annotations within the pipeline when parts of the pipeline are okay to fail, or when it's not. And so a lot of design decisions can go into this. This can be modeled in a variety of ways. Another one is latency budgets. Yes, we can limit when a service call should time out. We can define when a service should return a timeout. But in this case, maybe we want to group this together with other actions that are happening to ensure that parts of the pipeline provide a low latency at any given time. Another idea is to move away from pipelines being defined in Go code and define them in a different format, maybe more language agnostic, like YAML. And this is not because we don't like to write Go code. It has more to do with the idea that it would allow us to define a format where we can load and modify pipelines dynamically at runtime. That might sound crazy, but there's a good reason to do that, because it might make it easier for users of the platform to test new pipelines, new algorithms. So we want to focus on reducing the overall barrier of providing new functionality. Okay, let's summarize. What did we learn? Because I will quiz you about this in the next break. Not even joking. We have learned about essential and accidental complexity. Essential complexity is the actual problem we're trying to solve. Accidental complexity is just life, but we can improve it. A recommendation system is a multi-step process of generating content for the users. And the ranking system we built at Reddit was inspired by Unix pipes, all driven by a powerful single method interface in Go. Developing a platform means to have other engineers contribute to your code base in a way that makes sense to you, but most importantly to them. Thank you so much.